Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it: planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist. I'm with Tom Wagner, and today it's about our own home planet, Earth. You know, I think many people don't realize that NASA really is not only exploring space beyond Earth, but we're studying Earth as a planet in its own right. And we're doing that because it allows us to make life better here on Earth. So Tom, tell me much more about what Earth science is all about here at NASA.
Yeah, so the biggest thing with Earth science at NASA is we're trying to understand how the Earth works as a big system. That is, how all the parts knit together. And to do that, you need things like satellites and aircraft that can cover the vast distances that cover the planet, so you can see how change in one place is connected to change someplace else.
You know, the Earth has done nothing but change over time. You know, from a planetary scientist perspective, it's, can be billions of years. That's how we look at it sometimes. But, in reality, NASA's seen Earth and looked at it from space, and it's changed even over the last 50 and 60 years. What are some of those changes you see?
Yeah, so one of the biggest places, and actually some of the first satellite data that was collected about the Earth, was about the Arctic sea ice, where they used rockets to take pictures of it back in the 60s. And now what we've seen is that over the past 30, 40 years, we've lost something like 80% of the ice that used to be there by volume. And it's an amazing change. It's like turning one of the big knobs that controls the Earth as a machine.
You know, that water's got to go somewhere. What are some of the missions that look at that, and what are they telling us about where that water goes?
So there's a bunch of different things that we do. One of them is we use satellite radars to look at how fast the ice on the land, like in Greenland and the Alaskan glaciers, is flowing into the ocean. We use satellites like GRACE, which measure variations in mass at the Earth's surface. And then we have satellites like ICESat and ICESat-2, which we're going to launch later this year, which look at the height of the ice and how it's changing.
You know, in addition to looking at our water resources and other things, we really look at the atmosphere, and that means its dynamics and all the kinds of things that happen to the Earth with natural disasters. You know, how does NASA study and provide information about earthquakes and hurricanes, floods and wildfires?
Yeah, so one of the important things NASA does is try to develop the next generation tools so we can better forecast those events and when they happen, so we can do a better job figuring out what the impacts are. And the kinds of work takes all different kinds of approaches. So with hurricanes, we'll look at those with satellites. We'll also fly over them with aircraft that map the structure of the hurricane so we can figure out its power and the direction it will go in. And we work closely with NOAA on work like that. When there's something like a terrible oil spill in the ocean, we have special radars we'll put on planes to go out and map the extent of the spill, because that's really hard to do. And when it comes to even things like earthquakes, we use satellites to map the motions of the plate so we can get a better understanding on how the Earth moves and where earthquakes might happen next. But it all comes together. We even have a program that specifically looks at natural disasters and looks at how we can best support the other agencies that are delivering the aid.
You know, one of the things that really is so important that NASA does is using those assets in a very quick response capability. We get access to that data and we get it distributed, and it gets it to the right places are so important. How do we do that?
You know, right away when there's an action like that, the messages come into NASA headquarters to the person who is the disasters program manager. And right away, they rally the scientific community. And that's people from the NASA centers, but also from academia, to figure out what are the best things we can do to help. One really good example was the Nepal earthquake that happened last year, where they got together, particularly even to look at things like landslides, because it's not just what happened during the initial shaking, but later on when you get rains, how have you changed the landscape and where you're likely to get landslides?
You know, your area of expertise is in the cryosphere. What does that mean, and what do you do exactly?
Yeah, it's kind of a fun job title. You know, it's nice to be in charge. Well, technically, I'm in charge of all the ice on the planet. And I work really closely with colleagues at other agencies like NSF. But we're trying to understand how the Earth is changing as a system. One of the biggest ones is How are we losing ice from places like Greenland and Antarctica, and how is that contributing to sea level rise? And then also, how is the sea ice changing in the Arctic and Antarctica? And what does that mean for us as a planet? And then we're also doing things like looking at ice and snow in the Himalayas to understand how water resources are going to be affected for the billions of people who live there as the planet continues to change.
One of the things that we've uncovered is that in the Earth's past, it's gone through various stages, and in one of the stages we call snowball Earth. What can you tell us about what happened during that stage in our evolution?
Yeah, and that's a pretty exciting time. You're talking about going back, hundreds of millions of years ago to when the planet is frozen solid from the poles to the equator. And probably what happened was you had a time when carbon dioxide was drawn down so low that the planet got cold. But now the big thing is, once you freeze the planet over, and we have good evidence of that from things like glacial striations that we find on rocks from those periods and other things, how do you get the planet out of it? Because ice reflects almost all of the sunlight that hits it back into space. It's like a perfect mirror. And so one of the theories, though, is that eventually volcanoes generate enough CO2 to begin to warm the planet up so that ice actually melts. But it's a good example of how we can apply the same principles we see operating on the Earth today back in time to understand how the planet changed and evolved.
That snowball Earth era reminds me of several objects in the solar system now that we're trying to study, one of which is Europa. Europa's got this fabulous icy crust over the whole moon, and underneath it, perhaps as much as twice the volume of water than exists here on Earth. So the study of ancient Earth during these phases might actually inform us as to what's happening in some of these other planets and moons out in the solar system or at other solar systems.
Yeah, and another thing is the techniques that we develop to study ice here on Earth also apply to Europa. Like the scientists that work on radars that are going to go to Europa to map the structure of that ice. They're some of the same scientists that work in Antarctica today to help us map the ice and the bed underneath the ice. Some of the theories we've developed for how the ice changes, how it calves, how it breaks, they also apply on Europa. It's colder and it's a little bit different, but it's the same basic principles. And what I think is some of the most exciting research going on today are people that are drilling through the Antarctic ice to tap the watery bodies that are underneath them. Some of those are locked on land and they're not in connection with the ocean, and they've been separated from the atmosphere for many millions of years. And so some of even the astrobiology and origin of life crowd is interested in those. And then there are even projects, you have places like the Ross Ice Shelf, which is the size of France, where the massive glaciers of Antarctica flow into the ocean and float. And I know the planetary science community is joining with the earth science community to make a probe that will go through that, many hundreds of feet of the ice, get down to the ocean and sample it, and then come back to the surface. And that's exciting for planetary science as a prototype. But it's also exciting for earth science because, this place, no one's been there before. We have almost no exploration of it. And I think it's a really good joint effort.
Yeah, I do too. The Antarctic is such a special place. And you've been down there many times. What is it like?
Yeah, so for about 5 years, I was the program director for Earth Sciences. And what was neat about that job was if it didn't fit in another program, it was definitely Earth Sciences. So we got to cover everything from ancient dinosaurs to modern mummified seals to earthquakes, which Antarctica has plenty of, and volcanoes and magma and all kinds of fun stuff. So going there was great. On one hand, you're kind of going to the land of the unicorns, right? Hardly anybody gets to get there. And the things that you see, you're touching ice that we used to talk about was, thousands of years old, like from the times of the pyramids and things. And then the life there was amazing. You have benthic environments that are dominated by soft-bodied creatures and then eaten by seals, and you have penguins hopping around. And penguins are these amazing things. One time I landed in a helicopter and a whole troop of emperor penguins started sliding and walking towards me, and they surrounded the helicopter, and we had to wait until they got bored and left.
So they were just exploring too.
They really like people. It's funny.
What are some of the new modern tools that are being used in studying the polar environments?
So there's kind of three different flavors that I think really cross over with planetary applications right now. We've actually been developing robots that will drive the great distances across the ice and make measurements like drag radars behind them to map the surface underneath the ice. And we've got some ones that have even gone like 1,000 kilometers already. And it's really a promising area for us because these areas are just so remote and so challenging and so dangerous to work in. And you need precise, accurate, high resolution information that only like a ground survey can provide in some cases. So robots have a real great potential for us. But we also work in the air, and unmanned aerial systems are things that we're using now over sea ice and land ice at all scales. In some ways, some of the most amazing research is going on with small aircraft where people are using those to map the surface in a whole range of ways. And then finally, undersea exploration or under ice exploration is really one of the next big areas where what we need to do is understand the flux of heat between the ocean and the ice to understand why it's breaking off and melting and going to the ocean so fast. And some of those places, you can't go up next to them with a boat because an iceberg the size of the US Capitol building might calve off on you. And one of the only ways to do it is with submersibles that are autonomous. And also under the sea ice in the Arctic, you need to be able to go great distances and make all kinds of measurements. And so just like in the planetary science case where you need to operate in a remote location, something that's got some autonomous behavior, that's what we really need too.
What have you learned as an Earth scientist that would surprise most people?
I think the number one thing for me is that I think people view the Earth as this incredibly huge thing. And they don't understand that we as people really have the power to fundamentally reshape it. And we have, we've really affected the Earth as an environment for everything from, changing the landscape, changing the ecosystems through to changing the composition of our atmosphere and changing the temperature of our planet. And I think that that's probably that profound shift is one of the most important things that we've learned through our study of the Earth in the last 100 years.
Your work at MIT where you graduated was on volcanoes of not only the Earth, but the moon. Now, how do volcanoes play a role in the conditions here on Earth?
Yeah, so volcanoes are really important, in some simple ways, right? Volcanoes refresh the soils. They bring up all those nutrients and things. They have an eruption, and as they weather, they create great soils to grow crops in. They're kind of that returning, recycling of the Earth that's going on. But on top of that, too, they play a large role. They affect us through things like natural disasters. Volcanoes are a lot of times great places to live because of the soils. But on top of that, they also really fundamentally affect the composition of our atmosphere and some of the other characteristics. They constantly release CO2 into the atmosphere, which can cause the planet to warm. And on top of that, volcanoes can throw particles in the upper atmosphere, which causes the planet to cool. And for us that are trying to understand the Earth as a system, we have to include the effects of volcanoes are so great that if you want to do something like interpret the Earth's temperature record, you have to understand what the input of volcanoes were. And every couple of decades, we get a massive eruption that really changes the planet. Might even make it cool for a couple of years.
Well, it also generates a lot of CO2, isn't that right?
They are constantly releasing CO2 into the atmosphere. And they are, if you think of the billion-year cycles that go on the Earth, they are the component that drives CO2 up. And then it's weathering of rocks. As rainfall comes down, it scrubs CO2 from the atmosphere. That CO2 reacts with rocks, and it actually produces things like critters secrete, like the Bahamas banks, and other processes do that. And the volcanoes kind of bring it back up when it gets drawn down. But one thing to understand is that the scale of that process, it's so profoundly slow compared to what we've done as humans. Like that operates on the, tens to hundreds of millions of years compared to what we've done in a pretty short time.
The volcanoes here on Earth and the release of CO2 and other particulates in the atmosphere remind me actually of Venus and what we think may have been happening on Venus for so long. And that is, it is very volcanic. There's still some hot areas on it, and it may be still releasing an enormous amount of CO2. So what's the difference between Venus and Earth when you look at that?
Yeah, one of the things I love about Venus is also you see these funny volcanic structures, right? Like haystack things. And, and as I understand it, even, some of the fundamental ideas for thinking of the Earth as a greenhouse came from studies of places like Venus. It's another case where I think, the planetary science has given us kind of a wonderful example. But also, too, the terrestrial planets, a lot of the processes that run on those, on the Earth and on Mars and on Venus, and even the moon, are pretty similar. Like the fundamental processes by which you create magma and what the composition of that magma is. Now, the planets have slightly different histories because of their different compositions, but the overall principles that govern them are the same. And that's why you'll find a lot of times the scientists who work on volcanoes on the Earth also work on the other planets too.
Yeah, I'm constantly being reminded that what's happened on Venus can happen on Earth. And so we need to study these terrestrial planets and understand their evolution, because we're all evolving, even today.
Yeah, good points. And I also think too, sometimes what I think that what I want to say to kids and people who are listening is that, Earth sciences, planetary sciences, they're really fun detective mysteries, and they're just kind of inherently interesting. Like, hey, we found this weird looking volcano on Venus. What the heck made that? How would we go about that? What kinds of things would we do in the laboratory? What kinds of places on Earth might we explore to sort of understand that? And then, hey, ultimately, what kind of mission can we fly to a place like Venus to try to understand it?
So what's coming up next in Earth science in terms of the satellites or the missions or the real important themes to study?
So we got a couple of great missions coming up even later in the coming year or so. The GRACE follow-on mission is going to occur. And the GRACE mission was a pair of satellites that orbit the Earth that very precisely map variations in mass. And they've been used to do everything from figure out how much ice we're losing from the big ice sheets to even understanding how there's a cycle to the way water is stored on the land that is so great it even affects sea level. And so that mission will fly. I think it's going to launch in May of this year. And then later in the year, towards the fall, we're going to launch ICESat-2, which is a LiDAR. Think of it as a laser altimeter in space. It's a very special one, though. It's going to have 6 beams mapping the height of the Earth all over. And we're in particular going to look at the thinning of the Arctic sea ice. We're looking at the change in the height of the ice around glaciers and ice sheets around the world. And we're also going to map the height of all the trees on Earth with an idea of figuring out how much carbon is tied up in all the terrestrial biomass.
Yeah, it's those kind of things that are fundamental measurements that can provide us an enormous amount of information about the global Earth itself and understanding its biosphere and how it changes over time. So I'm really excited about those upcoming missions, and the technologies that are developed for Earth science missions can indeed be very important for planetary missions too.
Oh, yeah. It's a lot of the same kinds of sensors, and it's the same technologies that you apply to both places. I think with planetary, we have this additional challenge, right? Because it's far away and sometimes you got to shrink them. But, and one of the other amazing things, though, I think people forget about, and the problem with the Earth is we got this great atmosphere with clouds, that protects us in a lot of ways, but it's tough to see through. So you get a little lucky with some of the other planets where you don't have those things. But what I'm always amazed at is like when I worked in Antarctica and I was in the dry valleys, we would go out and map some of the local rock glaciers. That is places where there was rock held together with ice that was slowly flowing. And I met some of the scientists who worked on Mars, and they got some of their ideas for interpreting pictures we had of Mars from working in the dry valleys with some terrestrial scientists.
Yeah, you're right. Earth analogs are just so important for planetary scientists. And I know they haunt some really exotic places just to do that. What's your favorite image of the Earth from space?
Oh, so I think that my flat out favorite one is we combined some Landsat images together to produce a map of Antarctica that showed all this amazing blue ice flowing around rocks, and you could actually see the deformation structures of the ice, and it was really amazing. It's also one of the areas where we found the meteorites that we think came from Mars were actually found not far from there, so there's a good planetary connection too. But that's one of my favorites.
Yeah, indeed, from a planetary science perspective, the Antarctic is just a fabulous place to look for meteorites. We go down there every summer, line up a series of snowmobiles, trek across the glacier, and it's blinding white because of the reflected light of off the snow. But indeed, these black areas, you go to them and there's a meteorite. And so we tag them and bring them back. And sometimes we'll bring anywhere from 600 to 900 of them a season back.
Yeah, it's a fantastic program. You know, as they always said to me, they were like, well, if we're out in the middle of nowhere on the ice and we see a rock, we know it's a meteorite.
Yeah, that's right. That's the principle. You know, one of the iconic pictures for me as a planetary scientist is the one that Carl Sagan had the Voyagers do. It's called the pale blue dot. Do you remember that?
Yeah, and it's, you know, for me, that picture of the Earth, you know, so tiny, so far away, it's really important to put things in perspective. But one of the things that I've also always loved as a scientist, and someone who's crossed into planetary a little bit from Earth, is the cosmic zoom idea. You know, and the idea that, like, hey, sometimes here on Earth, we can get narrowed down to looking even at nanoparticles and smaller things, you know, in any part of the Earth system. But you pull back sometimes and think about, you know, here we are as part of this kind of larger galaxy and universe, and processes, you know, that happened in stars like supernova have even generated the little bits of iron that are in our body, and it's all connected up.
You know, one of the things that I asked each of my guests what their gravity assist was, that activity or event that occurred that really propelled you to become the scientist you are today.
So my mom says that when I was a little kid, I grew up with rocks in my pockets. She was always taking them out before she put them in the wash. And I knew I wanted to be in science. You know, I was the kind of kid that always had microscopes and slides and was doing things. But I think really when I got to college and I took my first Earth Sciences class, and it was in the 80s, and it was in that period where we were switching, you know, from old school kind of geology to sort of new school Earth processes. And I had a really great professor, Tim Lowenstein, who still teaches there, who was like, hey man, the Earth is this great big interconnected machine and we're trying to understand it. And that was really the thing that gave me my sort of pull to get into the field.
Well, what I'd tell you now is go back and look at those rocks your mom collected out of your pockets, because one of them might be a meteorite. Well, join us next time as we continue our exploration of the solar system. I'm Jim Green, and this is your Gravity Assist.